So as they take their seat, I'll just make a observation. You know, I came to the world of resilience from a very different background. I was a judge, and then I was invited to join the Department of Homeland Security as the senior counselor to Secretary Napolitano at DHS. And frankly, I'd never really trafficked in the world of resilience or even used the word much. And at one point in my career, I decided this is a pretty interesting word. What's the history of it? And etymologists will tell us that it's from the Roman word, the Latin verb, resiliere, if I'm pronouncing it correctly, to leap back. And then in 1626, Francis Bacon, he's a polymath, a philosopher, uses it in writing for the first time. And then in the 19th century, the timber industry decided, oh, well, timber, when it's loaded, has to bounce back, and they started using the word. And then, of course, engineers really adopted the word in their work. But if you look back just in the last 2 decades, there's been an explosion in the use of the word resilience. A Google search showed that between 2000 and 2013, there were about 525,000 uses of the word, Google Scholar. In the next decade, between 2013 and 2022, it jumped to almost doubled. So we've seen in psychology, ecology, everybody's using this word resilience. And it has many different definitions. And I see Ann Cosmel here, who worked with me in the federal government. And we used a number of different definitions along the way, as I know engineers have. We have centered on several. But the word is one thing. Achieving it, no matter what our definition is, we kind of all understand it, is a whole nother thing. And that's the focus of our panel. These experts have focused on actually implementing the word resilience and getting to something that achieves resilience. And that's why it's particularly exciting, because it's easy to traffic in the world of using the word resilience and ideas, but it's a lot harder to get down to the ground and actually do this. So I have wonderful experts. I'm going to first turn to Dr. David Frost. David is the Elizabeth and Bill Higginbotham Engineering Professor at Georgia Tech and a founding member and co-chair of the GEER Association, an NSF-sponsored organization that responds to geotechnical disasters worldwide. And before I go further, I should ask you, Sissy, do you want to say a few words? Go. Okay, good. All right, great. Go ahead. Yes. Dr. Frost. No, absolutely. I'll go sit over here. Thank you.
Oh, yeah, good. No, I'll just use the down. So first of all, thank you to the organizers, thank you to Sissy for the opportunity to come here and tell you a little bit about things that have been occupying my life for 30 years or 25 years, something like that. The sort of title that quasi was imposed on me was Against All Odds, and I thought, okay, how am I going to link that to what I'm going to do? And then I realized that it may not be if we work with nature, and so there's a theme of trying to work with a little bit with nature through what I'm going to talk about as well. More importantly, I'm going to use 5 quick case histories to give you examples of, based on reconnaissance missions that the GEER Association did, where we actually are able to see resilience and perhaps raise some questions about how we're utilizing the word resilience against the historical definition. So let me quickly start though and say that, you know, all disasters follow a source path site model, and I realized that we had quite a diverse audience in here, so I tried to snag an image that would sort of show you and and share that thought with each of you. And then maybe on the right-hand side, I just highlighted in particular that here's a site, some kind of an embankment, but there's actually multiple paths at that site. You can overtop, you can have through seepage, you can have under seepage, and so on. So while it's nice to sometimes simplify things and say that it's source path site, there's a complexity at each of those, the source, the complexity at the path, and the complexity at the site that we also need to not lose track of. I'm going to start my GEER examples by back in 1999, and I was much less gray hair. I was on a team that went to Kocaeli earthquake, Turkey after the Kocaeli earthquake. And one of the images, I didn't take this one, but it was an image that absolutely fascinated me, and I've used it a number of times since. You can see that there is a mosque and an apartment building right next to it, and then all around the apartment buildings there are piles of rubble, which were other apartment buildings that looked exactly the same as the one next to the mosque. Now, I'm not a structural engineer, but if you just ask me at a first blush to look at that mosque and ask me which do you think is the most vulnerable or the least resilient part, I would have probably said it's the minaret. And yet look at what is standing after the event. And so my question to you then is that there are basically two resilient curves there that I can generate, or they're schematically shown here. There's the black one, which is basically the resilience curve that's for all the surrounding buildings, and I don't have a finite time there, but presumably they rebuilt the apartment buildings, maybe not exactly the same. But if you actually look at the dashed red line, that's the resilience curve for the mosque and that one building that's right next to it. So my biggest question is if you had visited that location before the earthquake, would you have predicted the outcome that's shown in this picture? And I think that's something that we need to do more and more. My next one is I'm jumping to China, to the Wenchuan earthquake. And you'll have these slides, so I won't spend a lot of time in it. But the short detail is to say that there was co-seismic landslides that occurred. This is the image on the left, and that was on May 12, 2008. And there was about 50 million cubic meters of landslide debris moved during that earthquake. And within 4 or 5 months, there was a heavy precipitation event, and there were some debris flows came, and you can see in the second picture from the left, down in this region here, this is where the debris actually reached the river at the base. And so they realized we need to do something. And so they implemented the classical, what I call confront nature solution. Let's build big concrete check dams. And so when the debris flow is happening, we'll stop it. And they were designed, the check dams, they implemented them. They were designed to have a 30-year capacity based on the historical pre-earthquake scenario. Within 2 years, there was a large debris flow that involved 3.1 million cubic meters of debris. The check dams were completely obliterated. It was a completely failed system. And some of the images on the right there are just actually showing the consequences of that. And so if I say that what they did was they implemented the check dams, this was their resilience curve. In fact, I'm being generous showing them that there was even a recovery after it. Well, you don't have to hit them twice with a hammer to say you need to do something different. And so what they did was they said, well, let's revisit this problem. And so they came up with what they called a debris flow mitigation system. This happens to be in a location called Wenjia Valley. I visited there many times and participated in parts of this study. And essentially what they said was, if you have a debris flow, you need two things, water and solids. And if you don't have one of them, or if you don't have an abundance of one of them, maybe you don't have debris flows. And so they decided, what about developing a mitigation system? In other words, they wanted to work with nature. They knew they couldn't stop rainfall. They knew they couldn't stop the fact that there was debris there. But if they can somehow control this better. And so there's three components to this. Towards the top of the mountain, and I've highlighted in red there, they actually basically put in a big drain, a big grate. And so before it even gained momentum, they basically pass the debris over a grate, the water drops out in the bottom, and they bring that separately down through the mountain in a tunnel, all the way down to the bottom. So now, you've already broken up one of the sources of the debris. Then they had some additional methods that just were for, it's kind of like the braces and the belt. So they added a few things to say, okay, we need to also maybe dissipate some additional energy, and they used some systems there. And they still did put a couple of very simple check dams at the bottom, but those were designed to catch massive boulders that somehow may have made it all the way down to the bottom. And here it's a schematic, but this is 12 years later, this is the resilience curve of that system. And they've had many heavy rainfall events, and every time the system has held up and they have not had debris flows. So why is that happening? Well, apologize for the small size of this plot, but all of those lines in the background represent the relationship between duration and intensity of flow. And so generally debris flows occur when you exceed some relationship of intensity, so very high intensity, short duration, or low intensity, high duration. And what they succeeded, and then by the dark inclined line here, this is that gully before the earthquake, and after before the mitigation system, and after the mitigation system, this is the curve. And so you can see that essentially by implementing the mitigation, what they did was they made it independent of duration and intensity of rainfall, because you're taking the water out of the system. And so what's important to recognize about this is that the mitigation didn't just address the capacity issue, it also reduced the demand. So we have to think about more smartly about some of these systems that we work with. My next one is a fishing village in Japan. This is Utasku. In 2010, this is a picture of the village. 2011, 3 months later, this is the same picture. I've tried to always take my pictures with some reference mark, and this in this particular case is the arch going up to a temple. This was 2011. You can see there's nothing left there. It's completely obliterated by the tsunami. 2016, I went back, and you can see that now they've started to do some recovery. There are buildings or shops, temporary shops on the left-hand side of the image there. The road is reopened back up. 2018, I go back. The shops are gone. The temporary shops are gone. They now are moving along in their return to full performance. And there's some grasses growing, and nature's obviously participating in the resilience as well. And then in 2024, here it is. And by the way, that brown area in the front is not construction work. That's gravel, pea gravel, that is designed. This is the final condition. And in the middle of the image there is a playground for kids. So they have essentially completely changed, and the road orientation and elevation and everything has changed. Here is sort of a set of resilience curves representing that. So you had the 2010 pre-event, the 2011, and then the 2016, 2018, and 2024 sort of represent the different levels of resilience that they put together in the recovery. One was partial, one was perhaps back to full recovery, and then the other one is what I might call a transformational recovery. The key question here is was the true pre-event, pre-tsunami resilience understood and known? And that's the key issue here. Moving to India, northeast India, there was a glacial lake outflow in October 2023. This is a view of the dam on the Teesta River. The dam is a hydroelectric power dam. It's on the right-hand side there. You can see the water back upstream behind it. This is close-ups of the dam after the glacial lake outflow. It completely overtopped the dam. You can see that even though it was a substantially concrete dam, it's gone. There's just a gaping valley there. And in fact, even just to highlight it, the image on the right, you see that boulder there? Just for scale, that boulder is 15 meters, 45 feet. The power of Glofs and when there's debris in flow is unbelievable and impressive. So downstream, of course, there was also then catastrophe, because once the dam is gone, you've got problems downstream. Here is basically right now what I would say is the resilience curve for that Chungtang Dam, in that showing in 23, right after the event. And as of 1 month ago when I was back there, we're not still heading back up the recovery side of there, so I've put a dashed line to say that who knows when it'll be back up. There are plans to get there, but it's certainly catastrophic. coming a little closer to home, Helene and Milton. This is a map of all of the counties in the area impacted by those hurricanes. And you'll notice that I've got 8 of them colored in blue. I'll come back to those in a second. But first of all, we're used to thinking of hurricanes as a coastal problem, but Helene represented a variation on this in that it impacted coastal Florida, and then it impacted western North Carolina, and obviously places in between, including Georgia. I'm not dismissing my own state. But what's important is that the event characteristics and consequences on the coast and in the mountains were quite different. And while this might be considered a rare event today, I actually am pretty confident that this is going to be more the norm as we go forward, and we have to be ready for it. And so just when we thought Helene had happened, Milton occurred as well, so that was the cascading part of it. And so we also need to think about not only double hit events, but cascading subsequent events. So I apologize that they're small, but again, so you'll have the slides. Here are those 8 counties, and I have drawn the power outage curves for each of those counties. In other words, that's a resilience curve of the power systems. And you can see that they're sort of geographically, spatially located. So right up at the upper left is the one that was just sort of past the end of the impact area. So there was a very small outage, but nothing significant. And as you work your way down and you look to the left and to the right, you sort of see multiple things happening here. First of all, in those upper ones, you don't really see any effect of Milton, because Milton was down in South Florida, whereas Helene had passed all the way up through the other states. But then also what you'll notice is that there are 2, in certain counties, particularly as you get down to sort of the region between Helene and Milton, there are certain counties, there's a double spike because the system had not fully recovered, or it had partially recovered, and then it was hit by a second hurricane. And so the data that we now have, for example, for events like this is absolutely impressive, and we need to take advantage of it. By the way, if you take all of those resilient curves, and we did an area under the curve calculation, and you color code them, and then color code the counties according to that, you'll notice where the path of Helene is, and you'll notice where the path of Milton is. You've heard the story that says if you want to be on one side of the hurricane, you should always be on the on the left-hand side. There's less damage. Here's proof of it based on the resilience curves of the energy for each of those counties. Essentially, the red is to the right of the Helene curve. So they certainly reinforced that resilience needs to be both understood, both spatially and temporally. So in summary, I've shown you sort of a set of resilience curves. This was the mitigation system at Wenjia Gully. This was the tsunami village in Japan. This was the dam in India. And the one thing I'm going to add here to the right is that I call this the GLOF unaware. They were just happy going along. They didn't really have a good measure of what is the resilience of the dam the day before the GLOF. But had they had that, then it's quite possible that this is what I would have been presenting to you as the resilience curve. They had taken some adaptation ahead of time. And by the way, adaptation doesn't mean build the dam higher. It could have been increase the spillway capacity. It could have been do something else upstream that diverts water, that catches water, provide an auxiliary spillway, things like that. So there are always engineering solutions that we can implement. But the bottom line is, yeah, we might have still had some sort of failure, but more importantly, we can come back up. So if I take all of that, let's revisit sort of our source path site model, but instead of sort of thinking a little bit about differently, saying for resilient systems, we also need to think about the before, the during, and the after considerations. So this is the classic resilience curve that a lot of us sort of think about. We're going along at a constant pre-event. We hit the event, and then we worry about how are we going to recover on the back end, whether it's going to be partial, full, or transformative recovery. Here is a different resilience curve that I'd like to put in front of you here today. And there are several important elements to it. First of all, in this area here, if we're instrumenting, we can measure the degradation. We can understand that maybe we don't have a constant baseline. I'm not saying it always is going to be below. Maybe it is in fact above it, but we don't have a constant. Then, based on that and analysis, we can predict we maybe need something more. We need to make a permanent adjustment to the system. It's never going to, in order to achieve a certain level of risk aversion and to not make sure we don't have to spend all our money on insurance, then maybe there's some permanent. But then we also say, but you know, maybe we can't build it to cover all events. But then maybe we need to think about there's also a temporary adaptation that we need to add to the system that may help us address those additional set of events. And finally, we can remove that temporary part once the event has passed. Think about flood controls and so on. And finally, we get back to what I like to think about is predictive adaptive resilience. And I'm sort of casting it here as a, I don't want to call it superior, but an alternative to just the partial, the full, and the transformative. And just to put it in very simple terms, I mean, here's a levee. The bottom image is maybe what we have. Then we had to say, well, we really need to raise the levee up, so we put that blue stuff on top of it, and that gives us a permanent addition. But then we say, well, but if the water even rises a bit higher, maybe we need something temporary. Now, a lot of times in our world today, we think about sandbags are a temporary. Well, yeah, that's a temporary solution. It's easy to implement. But also then what happens is at the end of it, we're left with a bunch of sandbags that are contaminated, and we have to find, so there's costs. So I think we need to start thinking about what are some other solutions that allow us to deal with those temporary adaptations. And the bottom line is I think we have an urgent need for predictive, adaptive, resilient strategies and solutions. And that's it.
Thank you, David. That's a really wonderful overview, and it's very exciting. As a former policymaker, I wish you could go give that presentation to those who are really deciding how to invest our dollars going forward, because we do need to have all the ranges of capabilities. So thank you. Next, we're going to hear from Dr. Will Veach. He will be here virtually. Will leads the U.S. Army Corps of Engineers Infrastructure and Installation Resilience Community of Practice. That's a group of over 400 professionals who help mainstream resilience practice into all of the Army Corps' programs and projects. He's also an expert on sea level change and a member of the American Institute of Hydrology. So Will, take it away. Thank you.
Thank you. Can you hear me okay?
Yes.
Okay, great. And I'm going to share my screen. So are you seeing my screen now?
Yes.
Okay, wonderful. Well, thanks everybody for the opportunity to be here today. I really wish I could be there in person, but unfortunately I have to do this virtually, but thanks for the opportunity, and it's my pleasure to talk to you a bit about resilience in action at the Corps of Engineers. And I'll give you an example from the New Orleans levee system, and then I'll be really looking forward to our discussion and questions at the end. So I'm glad that I went after David, because he just did an excellent job talking about all these resilience curves. And so looking at the upper left, when we talk about resilience at the Corps of Engineers, we use a very similar kind of mental framework. When you talk about the word resilience, as we heard in the introduction, the word is used everywhere, and it means different things to different people. And so we have to be very specific when we talk about resilience. What we mean is this ability to anticipate, prepare for, and adapt to changing conditions and withstand, respond to, and recover rapidly from disruption. And critically, resilience is a trait or an attribute, and it can be an attribute of a system element, or of a system, or of a project, or it can be an attribute of a person, or of a community, or of an ecosystem. So in all of those contexts, what we use is this PARA, prepare, absorb, recover, and adapt framework, where the more resilient the system is, the better able it is to prepare for disruption, absorb that disruption with minimal damage, recover quickly, and if done well, actually take the opportunity of the disruption to implement adaptations that can actually increase the performance over time. So many thanks to David for explaining that concept much better than I could. I also want to point out that because we are in the Army, we have lots of regulations and manuals, and all of these are available publicly. So if you go to our publications website, you can find engineering regulations, pamphlets, construction bulletins, manuals, and so forth that go into how we address resilience. And these are all your tax dollars at work, so please feel free to copy or use them as you see fit. So our strategy for making this happen in our projects, programs, missions, and operations is a multi-faceted approach. And we have to, first of all, translate science. We don't want our engineers to have to be scientists. And so we take the available science, we translate it into syntheses and things that make it easier to access. We develop policy and guidance, and we develop that with our external partners, such as academic partners, international partners, interagency, and so forth. We embrace uncertainty. We know conditions are changing. We also know some conditions are just simply deeply uncertain. We can't hide from that. We have to embrace it, and resilience is one of the best ways to address uncertainty. We create tools and methods to support repeatable working level results, and we have to have that effort scaled to the level that is appropriate for the project. So we don't just want to do analysis for the point of doing it. And then we have vulnerability assessments of both our built projects and also our authorized but unconstructed projects. So we understand where our weaknesses are, and we emphasize training and capacity building. Almost 20 years ago, coming up very soon on the 20th anniversary here, Hurricane Katrina was one of the agency's lowest points, I would say. And it was a failure of both physical systems and organizational systems. And it was a national tragedy, but something that we learned a lot from. If you start at the upper left and work your way counterclockwise here, we have different failure modes of different types that kind of emphasize different issues that existed in the system at the time. Now, it's important to remember that the system at the time was not really a system. It was disconnected parts, and it was not a completed thing. It was only about 50% complete. But the 17th Street Canal flood wall failed due to a deflection of the eye wall, a failure mode that was previously unknown up until it happened. On the lower left, the IHNC flood wall failed, possibly due to a vessel impact, although maybe the impact happened afterwards. It's hard to know. In the bottom center, we have floodgates that were flanked, where we had hard structures connecting to soft levees, and the water went around the hard structure and focused energy on the soft levee. You can also see a barge sitting on top of the floodgate there in the bottom center. And then on the upper right and the lower right, we have walls that were overtopped. So they seem to have withstood the water until the water flowed over the top and then eroded away the wall or levee. So all of these different kinds of failures led to a lot of soul searching and what we called the actions for change, which were how we were going to change as an organization and make sure that this kind of failure wouldn't happen again. Now, we don't have time to go through all 12 of these actions, although all 12 are important, but I'll just draw your attention to a few of them. Number one being employing an integrated and systems approach to design so that we are not just building pieces and parts, but rather thinking about the whole system. Number two, employing risk-based concepts. So this comes back to the flood risk that we're trying to manage, but it also has to do with things like cost and schedule risk and different sorts of risks that we can manage throughout our construction, design, engineering, and maintenance processes so that we know what we're up against and what we're trying to reduce. Number five, employ adaptive planning. And I think that comes back to the adapt part of resilience, that we can make sure that we're planning ahead when we're engineering things, and we can also engineer things that are able to be adapted as we learn more or as conditions change. And then 9 and 10 here have to do with risk. So effectively communicating risk to the public, make sure people understand that it is impossible to remove all risk, but we can drive it down to a societally tolerable level. But there will always be risk, and also to establish public involvement in our risk reduction strategies. So make sure that we're doing this in partnership with our local stakeholders and our other partners so that everyone gets to be publicly involved, significantly involved, I mean. So what are some of the features that have been incorporated now into the system post Katrina? Well, on the upper left, you can see armoring of the transition zone between hard structures and soft levees. So we've got now concrete pads so that when the water hits a hard wall and goes around it and focuses energy on the levee now has been built up so it can resist better that flow. Lower left, we have high performance turf reinforcing mattresses. So these are strengthening the turf, the grass, so that when splash occurs over levees or when a Mother Nature comes up with a storm larger than what we've designed for, that the levee may overtop, but at least it should be able to resist the erosion. Upper center, we have an eye wall, but with a splash pad behind it. So if water splashes over the pad, over the wall rather, it will land on the pad and again, prevent erosion of the levee so that the wall doesn't end up getting undermined and deflected. And then on the upper right, you have T-walls. And so T-walls are a much more robust approach to allow for resistance to overtopping and loading than eye walls. They were not used widely before Katrina because of the wider right-of-way that was required. But one of the lessons learned was that acquiring that right-of-way is easier to do before you construct than it is after you've built the system and it becomes valuable real estate. So T-walls are much stronger and much preferred in areas where you can have things like vessel impact or potential overtopping. The system that we have today is also much more of a true system. So we have a continuous loop now around the northern part of New Orleans and another continuous loop around the southern part of New Orleans. We have dramatically reduced the length of the perimeter by adding storm surge barriers and outfall canal cutoffs so that all of the interior canal system is no longer a part of the perimeter. You can also see in the lower left a safe house for the operators of one of the large pump stations. So we've thought this through so that now it's not just a close it up and get out of their system. We do have the ability for people to stay and be safe and be there to operate the system as needed. So Hurricane Ida came on actually the 16th anniversary of Hurricane Katrina. It was exactly the same date. It was actually the same date as Hurricane Isaac in 2012 as well. And the system performed very well. Now, of course, there are differences. The storm was not quite as large. It was also a bit more to the west. So the storm surge was more on the south side of New Orleans, where Katrina, the track was more up towards Mississippi. And so the areas that were affected were very different. But the south part of New Orleans is the part that was really unconstructed in many ways before 2005. So if this had happened in 2005, it would have been an utter disaster on the south side. But because the system was in place, it performed quite well. And in fact, on that northern side, or what we call the east bank of the river, it was really kind of a non-event. You can see that the loading was nowhere near what the system was designed for. But on the south side, it was getting close to the design, and it performed quite well. Now, I do want to point out, though, that that doesn't mean everybody was well served. We do have communities outside of the levee system, and particularly in the area called Laplace, there were people who flooded in 2012 and flooded again in 2021. So we're working on a new West Shore Lake Pontchartrain project for that area. But you know, we had a successful operation of the system, but the system doesn't cover everybody. So in conclusion, the way we define resilience at the Corps of Engineers is using this PARA framework. That application can be applied to an element of a project itself, a system-wide approach, or a community. The lessons that we learned from Katrina allowed us to incorporate resilient features into the system we have today, and that system performed very well, performed successfully during Hurricane Ida. And that resilient features address known vulnerabilities, they avoid repair costs, they reduce system downtime, and they allow communities to bounce back faster at lower government expense. And I think under the current environment where we're focused on reducing expenditures and increasing efficiency, I think the business case of resilience is a very timely topic, and I'm glad we're talking about it today. Thank you very much.
Well, thank you, Will. Let's give him a round of applause. Obviously, it's very exciting with the 20th anniversary approaching to know that so much progress has been made and that we have learned from the past, which certainly will guide us for the future. But it sounds like you've also learned that we also need to plan for the future where we'll have changed conditions, and that will keep us all a lot safer. So next we're going to hear from Dr. Nagar Alhami Khorsani. She is an associate professor at the University at Buffalo with research focus on structural fire engineering, performance-based design, and resilience of communities under extreme hazards. Now, her wildfire research has resulted in a framework for simulating fire spread in wildland-urban interface communities that's been applied to the Hawaii fires in 2023, and unfortunately, we've also had the big fires in LA this year. So very exciting to hear her work. In my experience, working in the insurance industry and in the policy area, wildfire continues to surprise us, and much more so than other perils that we've experienced more frequently in the past. So thank you.
Thank you, Alice. Good morning, and thanks to ASC, NOAA, and NEST. It's a pleasure to be here. So today I'm talking about destructive wildfires, the fires that reach communities and impact communities. And I just want to mention that compared to some of the other hazards we've been discussing yesterday and today, these wildfires, destructive wildfires, we've been seeing them more in recent years in the past, if you look at the data, in the past 10 years. And then we have less data and knowledge, although in recent years things have picked up, and we are now looking into how to address and what to learn from these previous events, and that's what I will be talking about today. So let me see, are these the slides? These are not the slides. Okay. That's fine. Let me see what's in here. Okay, that's fine. I can talk about these, but I'm just thinking how to frame it around discussions. Okay, so what we've been working on, it's about a workflow to quantify wildfire damage in communities. And this is a little bit heavier on the scientific side of it, so I'm going to simplify it. Right now, we basically have three domains. We have these wildfires that start on the wildland side, and then they ignite. They reach the community, and then they spread inside the community. Those are the fires that we are interested in. And for being able to simulate these events, we actually have to capture ignition inside the wildland. Then we do have fire spread models. This has been a lot of ongoing research for more than 20 years in the wildland. So we can capture the fire spread inside the wildland. And then when they get inside the community, that's where we do not have an established simulation tool. And that's what we have been working on in the past few years at the University at Buffalo. So our framework is called, our simulation tool is called SWIFT. Stands for Streamlined Wildland Urban Interface Fire Tracing. Another important point, and I want to mention that it's on the slide, is on the weather or climate model. So regardless whether you're in the wildland or you're inside the community, wind input is another important parameter that goes into these models and being able to properly capture them. And these fires create their own weather. You might have heard of this, especially in the wildland, where you have a heat feedback from the fire goes back into the air, and that creates an interaction that these fires create their own weather. So locally you get a lot of turbulence, and that causes also fire spread. Okay, so this is our framework. This is our simulation framework, SWIFT, Streamlined Wildland Urban Interface Fire Tracing. And it does have layers of information on structures, vegetation, and non-combustible, so roads, parking lots, any place that doesn't burn, and that actually helps slow the fire spread. There are two modes of fire spread. that are critical inside these communities. One is thermal radiation, and the other one's fire spotting. Now, you might have heard or saw it in the news during LA fires. These fire spotting, these are embers that detach from vegetation and structures, and they can, during windy conditions, they can travel miles. And when they land in piles, and they can cause ignition if they're still burning. And fire spotting is a major mode of fire spread. So let's see, in terms of wind input, we have looked at, because again, it's another important factor, we have looked at a range of possible ways to approach this. So on the research side, which is all the way to your right, we work with coupled weather fire models. This is the state of the art. We work with NSF, NCAR, National Center for Atmospheric Research. These are large eddy simulations. They're computationally expensive, but then they are able to better capture the local turbulence. Now, on all the way to the left is you could just use weather stations, basically real-time weather station data. In that case, you're going to have low resolution and both spatially and temporally, and that is important. But that is going to give you or enable you to run something really quickly in real time or faster than real time to be able to guide response when a fire is approaching to the community. And then in the middle column, we have worked with tools coming from, these are operational tools. So this is, for example, Missoula Fire Science Laboratory. It's basically, it has average resolution, temporal and spatial, but it's useful for risk assessment. So we have applied this approach to several cases. We have done 2018 Camp Fire, the Marshall Fire in Colorado, Lahaina Fire, and then recently LA fire. So the lessons we have learned, that's the theme for the session, the lessons we have learned is based on several cases. And we've got to the point that we've been able to validate the model, and that also helps us apply the tool now to risk assessment of real communities. So we have been able to, we're working with City of Berkeley and using the model to simulate their response of a potential fire for risk assessment and guiding them in terms of where the vulnerable area is and how can they apply the results to allocate the resources that they have. So this is the Marshall Fire. This one is a good case for us to look at right now, because as you can see, I'm going to use, let's see if you see my pointer? No. So you see a line right going through the plot. That's Highway 36. The Highway 36, there are structures around. Do you mind if I use the? You have my slides? Can we switch? Thank you, no worries.
Yeah, the same folder. What is the folder? What is it?
Don't worry about it.
Yeah, it was the
So there are two ignitions. This is for Marshall Fire, and you see how when it gets to Highway 36, there's a cluster of structures right there where they are actually commercial structures. These are not residential structures. They have large parking lots, and they're not made of light timber frames. So they're either masonry or industrial type structures. So what happens is that the fire, now you can see it, it's just reaching Highway 36, and it has to go around, so it's going up north before entering the community. So there are two communities affected. One is Louisville and the other one is Superior. And what you're looking at here is that so we have the simulation results. We conducted two simulations, one which is the realistic one you're looking at, and the other one would be one that around Highway 36 we would have regular structures, not what we call ignition resistant structures. And in the case that we didn't have any ignition resistant structures, the fire was able to go through Highway 36, past Highway 36, and damage most of the town. Whereas in the real case, because of those clusters of structures, they actually slowed down the fire at that point and made the fire go around and then enter the community from northwest. Which, comparing the two cases from the simulation point of view, we're looking at something along the lines of $1 billion in different losses. So in one case, we're looking at, in real case, in terms of insured losses, is about $1 billion. The other one, more than $2 billion. So the fact that this was not designed for, wildfire, but it just happened that they had this cluster of structures that actually helped them. We would see something similar for the 2023 Lahaina fire, not to the point that it slows down the fire, but again, the cluster of structures actually help to some extent change the path of the fire. So in this case, there is a village. There's an area, it's called Kahuma Village. It's newly built just about a year or two before the fire happened, so it's built to the code. Again, the code doesn't concern fire, but they have wind in Lahaina, and some of the detailing for wind actually impacted or worked pretty well for the fire case. So what's happening here again is right where you're looking at here, the fire, exactly at this moment. Again, there is a cluster of structures. This is, again, Kahuma Village. They were ignition resistant. So they only out of the whole blocks of buildings, only 5 got damaged. And the fire had to go around before being able to move towards the north of the city, which again, it still made, it was a disaster, created a lot of damage, but comparing a case where you do not have ignition resistant structures, whereas in this area the fire was the fire moved less with less speed. So I'll wrap it up here. Let me point out a few things that I had in mind. So ignition resistant structures. I kept talking about ignition resistant structures. What do I mean by that? In terms of houses, there are certain features of houses that lead to a structure to be ignition resistant. You're looking at siding, you're looking at windows. They impact thermal radiation. And then you're looking at roofing, you're looking at vents, decks, fences, if they're attached, and any combustible material within 5 feet. They call it zone 0. So all of these impact vulnerability to fire spotting. So when we say ignition resistant structure for a house, at least in the model, it doesn't mean that the probability of ignition is 0. It actually is, we reduce it by 50%. So individually for probability of ignition due to fire spotting is 0.3. Probability of ignition for thermal radiation is 0.3. So combined, your likelihood of ignition is down by 50%. Now this is for residential structures. We also look at commercial structures or anything other than residential. You can have structures made of concrete, steel, You have, again, large parking lots. So we look at the configuration, what's around the structure, as well as the material type. And again, it doesn't mean that they will not burn if there is a vulnerability, the fire enters. I mean, you might have seen images from LA fires. You have schools, hospitals, they get impacted, even if they're out of concrete. Yes, the concrete wall will be standing after the fire, but the fire gets in, it burns down the structure. So again, likelihood of ignition is down by 50%. Now, what the argument is that if you have these clusters large enough, then you will be able to slow down or change the path of the fire. And that's what we have been showing by simulations, to be able to quantify these vulnerabilities and be able to predict. The other point I want to make is that with fires, so with other hazards such as earthquakes, those of you who've worked with other hazards, even wind, you have different damage states. You may have slight damage, extreme damage. With fires, it tend to be binary. Either it burns or not. So when the fire gets to the structure, enters the structure, it's done. So again, even in the model, sometimes we get this question. It's really at this point a binary. If it gets ignited, it means that it's very likely that that structure will be burned down. And I will leave it as that. Thank you.
Thank you, Nagar, and you did demonstrate extraordinary resilience. You also pointed out something that I am seeing in the insurance industry, is that wildfire, because it is binary, and it's an unfamiliar risk and it's difficult to model. As you've just shown, we've learned a lot from what you've been able to demonstrate. It becomes an area that they're less willing to bet is a profitable area for them. So last but not least is Dr. Mabel Shadid. She is a geotechnical engineer with WSP. She's experienced in the evaluation of soil erosion problems. Her project involvement includes a post-Hurricane Sandy corrosion mitigation project at the World Trade Center and project management of a segment of Amtrak's Gateway program. At ASCE, she chairs the Professional Practice Council of the GI. So thank you. Take it away.
Thank you, Alice. And thank you, Sissi, for inviting me to attend and contribute in this very interesting workshop. It's been a pleasure. Okay, so at WSP, we have developed a highway infrastructure resilience framework to evaluate resilience by breaking it down into 4 different levels. So on this slide, we have 2 of the levels. The pillars will focus on the functionality and on the database PDI, and PDI stands for Post-Event Damage Inspection, and PEI, Post-Event Engineering Investigation. So this is the first level, and then the second levels are the lenses. For example, under functionality, we have robustness, resourcefulness, and rapidity. Now, the third levels are dimensions. Each of the lenses can have up to 4 dimensions. The technical, dealing with the structural performance of the built environment. In this case, we're talking about infrastructure. The organizational, dealing with the ability of the organization that manage the infrastructure to respond with the extreme event. And the social, which represent the ability to reduce the impact on societies and communities. And finally, the economical, and this is the direct and indirect damages and losses. The fourth and final level are the indicators. And on the slide, we have 16 indicators falling under their respective dimension, lenses, and pillars. And this is a simplified version of what we call the Resilience Evaluation Tool, or the RET, that we're gonna apply next in a demonstration test case. So here, the problem statement or the objective is to evaluate the impact of 2 alternative investments on the seismic resilience of a highway portfolio as compared to a baseline scenario, which is the do-nothing strategy. Alternative one is a structural retrofit of certain assets within that portfolio, the assets that will cause the most damage because of a higher exposure or because of aging and degradation effects that is reducing their seismic capacity. And we are estimating the associated cost of this retrofit as a fixed percentage, 30% of the construction cost of new and identical structures. Now, alternative two is the installation and the operation of a series of accelerometers and displacement sensors. So here, the focus is on the technological upscale or the instrumentation enhancement of this portfolio in order to collect the performance data along the life cycle, and in order to be able to trigger a warning to the operators in order to handle and be able to respond against the hazards. So the associated cost here is estimated as $2,000 per structure. Mainly, we have 2 accelerometers for every single assets within the portfolio, and an additional $150,000 for the implementation or the integration of a GIS-based and a web-based platform for better data management for the data that we are collecting from this instrumentation system. So now we're starting to apply the framework. Step one is to define your assessment scale. So here we're talking about portfolio of highway transportation bridges, namely 13 bridges in New York State, and define the exposure type. It could be a single hazard, it could be multi-hazard. Here we have a single hazard, an earthquake. So this table summarizes the bridges that the 13 bridges selected for this demonstration test case. Their construction year spans from 1936 to 2018. They have different structure types, different number of spans. Basically, we try to create a diverse portfolio covering a wide range of structural fragility and seismic hazard exposure. This is the location of the 13 bridges in New York. And then we move to step two, which is a risk assessment or a seismic risk assessment following the seismic loss estimation methodology by Haas's MH framework. It has 3 steps itself. So first we define the seismic hazard. And then based on this seismic hazard that we've selected and available fragility curve, we end up with what Negar has mentioned briefly, characteristic damage level. We have, it could be one of 5 levels summarized in this table, going from no damage to full collapse. And then once we have the characteristic damage level, we can estimate the direct physical damages through the damage ratio, and we can also estimate the indirect damages in terms of restoration times and loss of functionality. So after applying the loss estimation framework, we can see that the total direct losses for this earthquake hitting our portfolio is $6 million approximately, and the indirect losses are $2 million. Now, the bulk of the framework is applying the resilience evaluation tool on the baseline scenario and on both resilience enhancement alternatives 1 and 2. So we start by assigning weights on all 4 levels, the measure level, which is our indicator level, the dimension level, the lens level, and the pillar level. And the weights here are assigned based on their relevance and significance to the post-recovery of our portfolio as exposed to the seismic hazard. Now, after we have the weights, we start by scoring the indicators. So each indicator, each one of the 16 indicators that we've selected, will have a score from 1 to 4, 1 being the lowest resilience, 4 being the highest resilience. And in order to do so in an objective and consistent way, we have come up with measurement scales for each of the indicators. We're going to skim through them very quickly. These are the measurement scales that we've used in order to score our indicators. So now we have the indicator score, we have the indicator weight. Multiplied and summed up, they will give us the dimension, which is the second level from the bottom, so the dimension score. And this is how we calculate or we estimate a resilience score by going bottom up. So the dimension scores will be giving the lens scores. With the lens weights, they will be giving the pillar score, and finally we'll get to the overall resilience score. And the resilience score for the baseline scenario in this case is 2.1. And we can repeat this procedure again for alternative number 1, which is the structural retrofit. So it's making the structure more robust, so it's increasing the score of our functionality pillar, and it results in an overall resilience score of 2.8 as compared to the 2.1 of the baseline scenario. And now, same thing for alternative number 2, but in this case, we're talking about instrumentation and monitoring. So we're gonna be enhancing the lens that is about data collection and management. We're gonna be more prepared with automated procedure to deal with the hazard, and the score of resilience overall would increase to 2.4. There's one missing slide concluding. Basically, we've seen that with alternative number 1, the resilience score increases by 35% from 2.1 to 2.8, and by 15% only with alternative number 2. However, the cost of alternative number 2 is much less than the cost of alternative number 1. And here we can see how the information that we took from applying the framework could be used in order to advance and support decision making. Should we go with alternative number 1 or alternative number 2? And the results of the framework can, of course, be used in conjunction with cost-benefit methodologies in order to get to the right answer and make the right investment in this case. That's it. Thank you.
Thank you, Mabel. That's a very important work. One of the things I found as a policymaker is it was difficult, as I'm sure you found in your work, to have the decision makers decide to actually invest the extra dollars to make the structure resilient. Spoke to a number of engineers who said it just always ends up on the cut and ends up on the floor. Nobody's going to invest in it, but I think your framework will help improve that decision making and make it much more clear that it's a valuable investment to make. I want to turn to some questions now. I'm going to ask first you, Nagar, and David, if you could come back. I want to ask you, what are the urgent needs for engineering in the future hazard space, and how could lessons of successful strategies or observations you presented inform future codes and standards? So David, you want to start?
And you all have a microphone in front of you on the table if you want to use that. I have 3 slides or 4 slides that are going to come up.
You had the question first.
Yeah, no, we were pre-warned, which I think it makes it more valuable for all of you. So, yeah, I didn't move that. So I'm going to start here with a slide which was at the end of my last presentation, just to tell you that. So this is kind of that framework that I was putting out there and asking you to think about before, the during, and the after. Given that, I decided I wanted to bring it back to you as a real-world example, and I decided to use an 800-year-old example. So this is not new stuff. And I picked the Tower of Pisa. Now, if I asked most of you, what's the issue with the Tower of Pisa? You're going to point to the geotechnical engineers, and they're going to say it was a foundation problem. They screwed it up day one, and it stayed there. Well, maybe you're going to be in for a bit of a surprise. I'm also using it because the kind of problem we're talking about, sometimes we think about, oh, it occurred, and we're done, and we're fixed, and we need to be back in 2 weeks. Sometimes having a problem that's stretched out over a long time gives you a chance to actually digest what happened at various stages and then understand things better. Many people, as I think it was geotechnical failure. In fact, I might say that it was a compound geotechnical, structural, religious, art history, tourism resilience event. Not a failure, by the way. It has been monitored for its entire life, which is more than 800 years, and adaptations have been implemented periodically. The major adaptation in 1990 was because, in fact, not because of the foundation, but they began to realize there was a nearby similar tower that was almost vertical, collapsed. And that made them say, wow, what if we put a lean into the tower? Are we even at higher risk? And so it actually was a structural issue that motivated the major intervention starting in the 1990s. More importantly, the commission that they put together, the team, involved experts in restoration, mineralogy, history of arts, archaeology, structural and geotechnical engineers. And the important message in that for us is that, I mean, this is a milestone event in our history as a global entity. And they saw the importance of having multiple perspectives addressed in it. So the one question I would ask you sort of is, would you ever consider visiting the non-leaning Tower of Pisa? And that's important because it takes you out of, let's say, your engineering space and takes you into other reasons why the Tower of Pisa might be important. So here's a very brief history of the tower. On the upper plot, I'm actually showing the tilt of the tower. And you can see that from early on, there was a significant tilt started to grow. And by the way, the lower plot is just the weight of the tower as a function of time. And the x-axis there is 800 years, okay? That's not 2 weeks or a month or 3 months. That's 800 years. And so you can see much of the action actually occurred in the first 200, 300 years. Now, if you look at the upper right, here, in fact, is how they built the tower. They only built the first 4 levels. And then they did an adaptation because they realized they had a leaning problem. They stopped for 100 years. And then they came back after 100 years and they added 4 more layers. And then they realized that they had an exacerbated problem, so they stopped again. And it was only after another 100 years that they actually finally came back, a very gutsy individual came back and added the bell tower at the top of the structure. So there was an example 800 years ago, or starting 800 years ago, they were employing adaptation. They realized that if they just carried on the way they were going to have a failure on their hands. Now, this is the more recent 30-year period from the intervention, the commission, and I won't get into the details of it, you'll have the slide, but what you can see is it was moving, and it was continuously moving. And by the way, it was almost like any time somebody looked sideways at it, the tower said, oh, I'm going to move a little bit more. As I mentioned, the key issue for it was the fact that there was a structural failure of another tower elsewhere in Italy that catalyzed this activity. So if I come back to my resilience curves, this is the world that I think a lot of times we live in. We believe we have a constant base, and then we think about, well, there'll be a failure, and then we're going to come back at some degree. Well, here, we can't afford to be reactive. In fact, I've intentionally put not real in that photo in case some of you leave here and say, Frost showed a photo of the Tower of Pisa collapsed. Did it? No, it didn't. You can get any photos like this you online now. But more importantly, let's come back now and look at the history of the Tower of Pisa, at least the 30-year history, the recent history, in the context of that new resilience curve that I have presented to you. So here's the curve. I haven't put anything on it yet. But now, when they got to start to do the intervention, what was the first thing they did? They instrumented the hell out of it. There were more instruments on that you could possibly do. If somebody walked up the stairs on the inside of the tower, they could tell you, and they could tell you where you were because of various instruments measuring vibrations and all of that, and they were closely monitoring it. They needed to understand where they were at any time before they started messing around with it. I told you the tower would, if you look sideways at the tower, it would move, so you had to be aware. Then they implemented a permanent solution. The permanent solution was under excavation. So they're carefully removing very small amounts of soil from the side of the tower opposite to the direction it was leaning, so you could kind of get it to lean back a little bit. So that was the permanent intervention. Once they implemented that, there's no going back, but that was key. They were worried about making sure that they had short-term stability as well. So they did 2 things. They did a temporary adaptation. One, and this was for probably for the foundation people, they put lead weights on the opposite side of the tower so they could again have extra counterweight acting down on the side that they were trying to reduce the tilt from. And they also, for the structural engineers, and it's a little hard to see them, but they actually put straps around the center of the structure as a backup system. They were not tight, but in case the thing started to move a bit more, they were already in place. They had a secondary system that they could implement. Once they completed the under excavation, they removed those 2 temporary structures, and they came back And here is their predictive adaptive resilience state. And if you go today, you can see the tower. By the way, it has not moved in the almost 20 years now since they implemented that system. In fact, the amount of tilt they brought back was only about half a degree. And the reason they did that was they still wanted it to be the Leaning Tower of Pisa. The historians and the tourism wanted that. But more importantly, they wanted to make sure that they gained time. And by reducing that amount of tilt based on the history, they bought 300 years. Now, if it's continued to lean again at the rate that they went. And so quickly to answer the question, how can we implement and encourage this in practice? Well, codes and standards, we had lots of people suggesting A or B yesterday and so on. If you buy an automobile, you'll see this on the window of your car. And I want to zoom in on this. So many of you look at the price and that's it. But if you zoom in on it, there is a component of it here is ratings. There's a rating for emissions, there's a rating for smog, but there's also a rating for safety. And so ratings are something that society and people can accept and recognize. In fact, I was very pleasantly surprised and pleased to hear the presentation just before me, because what is that? That's a rating. It's a resilience rating they're computing. And I think the importance of that is that you can engage a lot more people if you have a rating than if you have standards and codes and things like that, because that tends to be sort of thought of as the domain of the engineers. I know that formerly Golder developed a system called GoalSet, which was the Golder Sustainability Evaluation Tool, and I suspect that's somewhere in the engine of what your RET is as well. But the whole purpose of that was so to be able to talk to communities and individuals, non-experts and so on. And I think we've got to start thinking about that as part of our solution. And with that, that's my answer.
Well, thank you, David. Wonderful. And Nagara,
Sure.
what's your response? You don't have to have a leaning tower.
Following David is not easy. Okay, so on the wildfire side, I'll start with the needs. I talked about physical damage to structures and houses, but I think we definitely need to go beyond and look at this as a system of systems. Yesterday we talked about lifelines. We cannot have resilience without functional lifelines. And with wildfires, we definitely have, water. We need water for firefighting during the event, and then unfortunately they get contaminated. And then after, during the recovery process, we have, issues. Transportation. We need functional transportation for response evacuation of people, getting emergency responders places they need to be. Power, they tend to cause ignition, so there's a mitigation action there. They also get damaged because of the power lines. So lifelines is one thing. The other need I would mention is that we need to look at these events and what we do at every stage, again, from mitigation all the way to response and recovery, in terms of the impact with other hazards. So not just a standalone, because looking at, this is the easiest example, LA fires again, you're looking at a region where it's prone to seismic as well, for example, and other hazards. So what you do, every action you take impacts different hazards. And now that the area is impacted by fire, there was a mention of compounding hazards. What if an earthquake hits, right? So we have to think, again, more broadly with effect of compounding hazards. And with the codes and standards, we know that we can build better, right? And there are activities in the code and standard environment. ICC is working on coming up with new standards. There are already existing standards being updated. So there's definitely activity there. And how we build, so we have this pre-event, during event, and then after the event recovery, but I want to mention this explicitly, that how we rebuild, let's say, LA is on the way to rebuild. Lahaina, even after a couple years, not many parcels have been able, they haven't really recovered. How we rebuild really sets the stage for the next event. And I mentioned this with fire. If you, David has been talking about, the capacity side and the hazard side. It's one of those events that if you increase capacity, because structures are the fuel inside the community, right? If you increase the capacity, you're not just increasing the capacity, you're also lowering the hazard, right? Because of the intensity. So if there are less number of structures that get ignited, it means that the intensity inside the community also goes lower. So bottom line, if we update the codes, we implement the codes, the way we build will impact the resilience. I will mention this though, that what's missing, again, looping back to the need, is we still do not know what thresholds of intensity are these measures effective, in a sense that, again, with earthquakes, we have different magnitudes, right? With hurricanes, we have different hurricane categories, right? With wildfires approaching to the community, what thresholds are we looking at? So building better will help, but we don't know yet at what threshold we'll be able to sustain. And at some point, it will burn again, right? Would that be acceptable or not? Something to investigate in future.
Absolutely. And I lived in Los Angeles for 25 years. As it turns out, I lived in a community. The first house my husband and I bought was in the FAIR Plan. I don't know if you all know what the FAIR Plan is. FAIR plans are in most of our, or about 36 of our states. They're government backup plans. If a private insurer won't insure you, the government will provide you an insurance policy. I moved from the East Coast. We bought this house right back up on a hillside, and the agent said, oh, well, you won't be able to get private insurance. You'll get insurance through this FAIR Plan. I was so new to the community, I didn't realize, wow, that means my house is really likely to burn because only the government insurer would offer it. And then I moved to a community that is now rated, USDA rates all communities across the United States for their wildfire risk. You can really almost get down to the parcel, and 99% more likely to burn, the place I lived in. But all that's there, it's built to old codes, and even the new code, 2007 in California, I think it was Camp Fire, only 50% of the structures built to the new code survived. Now that's good in comparison to the 19% that survived that were to previous codes. But that's not very reassuring if you're in the one half that got burnt. So we have a long way to go with wildfires, but I do think the resilience rating is something that's taking off in Alabama with the fortified homes and other things to show that this is insurable, plus it's resilient overall. So we have just a few minutes. I want to turn to Will and Mabel and ask them, what are the challenges for supporting resilience infrastructure investments for future hazards in practice? And how can engineers be better supported to move beyond code designs and innovate? So, Will, do you want to take it first?
Sure.
See with us? Good.
Well, yeah, I'd be happy to. So, great question. I think that we all understand the business case for resilience, that if we build resilience into our systems, we're not only being good stewards of the taxpayer dollar that we've invested in that system, but we've also reduced the need for downstream repair costs or lost effectiveness, and we can even avoid costs that come up through things like emergency response and rebuilding. That being said, I think one of the big challenges we have is making that business case, is actually making the justification. Because of the way we compute benefits for our projects, the savings that we're receiving are in the future, and the costs are today. So when you discount the future savings to net present value, it can be difficult to pencil out if you're just looking at dollars and cents. And so we have guidance within the Army Corps of Engineers that says we can justify these resilient features on the basis of saved life cycle cost, but it's much easier said than done, both in terms of the method and also in terms of just the math of a saved maintenance cost 20 years in the future may not really compare to an upfront investment. And by the way, I think this also applies to all kinds of maintenance. So I think it kind of results in a little bit of a perverse conclusion. It sort of implies that you shouldn't change the oil in your car because the failure will be sometime in the future and the cost is today. So I don't think this is a good way to make decisions, but it is a fact of the way that we make our investment decisions in many cases by considering economic costs and benefits. Now, how can we support people to innovate? I think one thing that we're working on right now, we're in the process of a revolution in the Corps of Engineers, is that we are trying to consider comprehensive benefits, other sorts of social and environmental benefits that we know exist but are difficult to monetize. And if we can figure out how to incorporate those into our calculus, then I think we'll have an easier time justifying some of these features. But what's tricky with that is the more flexibility you give people, the harder it is to achieve standardization and equity. And I think that what we're trying to do with comprehensive benefits is we're trying to make sure that we're considering all the impacts within a community. But ironically, what you might end up doing is creating more disparity between communities because considering those impacts costs more money. And so when you have communities that are willing to partner on a more expensive analysis, they may end up with a better analysis than a different community that wants the simpler approach. So I think more flexibility, more ability for engineers and other practitioners to use multiple lines of evidence to support their professional judgment and make a case for what they believe to be the right thing to do, rather than just a cookie cutter economic costs and benefits approach is good. But I think you have to be aware that the more flexibility you give, the more variability you may have to live with. So to me, that is one of the major challenges.
Excellent point. And I do think in all of this, as we see more extreme weather, we are also likely to see more inequality develop as we've seen some communities have the money to prepare and some don't. I will never forget speaking to a mayor of a small town in Alabama. This is, I don't know if Ann was there, but maybe in 2013, and she said she was the mayor of Perdido Beach, aptly known on the Gulf, subject to hurricanes, flooding, and she said, you know, I get it. I get that I have a growing risk here, but I'm a part-time mayor, and I don't have a planning staff. I don't have any information. How am I supposed to get ready? And unfortunately, that question is still not answered. And I think Will raises a really great point that there could be some communities that are left behind if we can't figure out a way to help them understand the risks and then make the necessary investments. So that was my piece, but Mabel, I'm going to turn it to you for the last word.
I'm going to actually build on your piece. You said it. It's information for me, the lack of data. And I think Marsha invited us yesterday to take a minute and think about data availability and quality and management. And I think it's got to be one of the biggest challenges we face for infrastructure resilience, for making the case for investment, because it's the foundation for the evaluation of resilience, and then for the evaluation of the alternatives that we are considering for resilience, for estimating the cost or the funding that we should be looking for and starting the procedure to kind of secure the funding. And it's a challenge here because we're talking about many scales in time and space, social scales, many disciplines. So it's an interdiscipline, and the way disciplines collect data and manage data is different. And also many stakeholders, the federal government, the federal agencies, the state DOTs, the local transportation agency. We have the engineering experts. We also have the public the public can help through crowdsourcing information. And I think having a consistent, standardized approach for collecting data and circulating data would help. It's already in place. We have many manuals for collecting damage data after an event. We have tables of damage data lists that we're looking for normally in the field, but this could go beyond damage data. We could also be looking at post-recovery or recovery after an event, the metrics of that. We could also look at the normal condition data, and this is how we integrate resilience in the asset management lifecycle through the asset data sets and through real-time monitoring. Another point that could help is the use of emerging technologies. Now, the challenge here is the funding again, the ability to purchase or acquire the new equipment and to train the personnel to use it. But if we can, it will, of course, make the data collection faster and safer during an event. And it would make the visualization much more interesting. So it would help us using GIS-based and web-based platform for better data management and for better data visualization. And one last point I'm going to touch on regarding data. We often focus on damage data and failure cases, but it's equally important to look at success cases. And I learned that from Sissy, actually, because like we said, in success cases, the structure has performed as intended, or it has exceeded the performance. So why don't we just investigate in that more and see what are the reasons behind that, and use these reasons to calibrate our planning, our modeling pre-event, and also use these lessons in order to maybe improve and update the codes and standards. So that's about data.
Well, thank you, and I think that's a wonderful note to end on, success, because all of our speakers have demonstrated that there has been success. I want to thank Sissy for putting together this exceptional panel, and I want you to join with me in thanking our remarkable panelists for sharing what they've done.